In the next example problem, we are going to begin considering the effect of an object moving along a ramp or an inclined plane. Now, very often in this course, we want to consider objects that are moving. We set up a coordinate system, and we almost always will choose the x-axis of our coordinate system to be horizontal and the y-axis of our coordinate system to be vertical. It turns out in many scenarios, this is the most convenient coordinate system to use. But this is not the most convenient coordinate system for every scenario. One example where we would rather work with something else is a ramp or an inclined plane. For a ramp or an inclined plane, we will very often want our x-axis to lie along the ramp and our y-axis to lie perpendicular to the ramp. So to have the x-axis lie along the ramp, I would draw the x-axis to be something like this. And I'm going to choose to have the y-axis be perpendicular to the ramp. I'm going to choose to have my crate start at the origin. If I wanted to, I could have my y-axis at the base of the ramp. That would be just fine for this problem too, but I'm going to draw it there for now. So here is the y-axis for this problem. Okay, so you might be wondering right now, why would we work with a tilted coordinate system? There better be some good motivation for that because it looks like we're making more work for ourselves. Well, to demonstrate why we are working with a tilted coordinate system, let's think about F net equals ma. So we have Newton's second law. This is really a vector equation. Now, when I am working with some type of vector equation, this is actually two equations in one. I have one equation describing what's going on in the x direction. So I could say f1x plus f2x plus f3x on and on equals mass times acceleration in the x direction. I could have a second equation that describes what's going on in the y direction. So I could have force 1 in the y direction plus force 2 in the y direction plus force 3 in the y direction plus however many forces I have in total in this problem. That's equal to MAY. Now, I'm being completely general here. I'm being vague about what forces are actually acting on an object. But the reason I want to bring this up is if I could set a lot of these terms to 0, maybe I could set f2x to 0, f3x to 0, maybe I could set f1y to 0 and ay to 0. If I could choose a coordinate system such that many of these terms just become 0, I'm going to make my math a lot easier to solve. So let's see if that happens with this particular choice of coordinate system. So now I'm going to go back into this specific problem and look at it. And I'm going to draw the forces and the acceleration of the crate. So we place a crate 30 meters up from the base of the ramp. The ramp has an angle of 20 degrees with the horizontal. And then the crate itself has a mass of 2 kilograms. I know because we are assuming that the crate is on a frictionless ramp. As soon as I place the crate down, it will slide down the ramp, and the crate will also pick up speed. In other words, the crate will accelerate along the ramp. The crate is not going to magically jump off the ramp or tunnel down into the ramp. The crate is going to move along the ramp. So the direction of the acceleration vector of the crate will be entirely along the ramp. So here is my acceleration vector for the crate. I could also choose to draw the forces that are acting on the crate. I know gravity is pulling the crate straight down towards the center of the earth. So the force of gravity on the crate will look something like this. So here's F gravity on the crate. And there is also going to be a normal force acting on the crate. The crate is in contact with a surface, The crate is not going to fall into that surface, so there will be a normal force. And from lecture, we learned that the normal force is always perpendicular to that surface. In this case, that means that the normal force is entirely in the y direction. So here's Fn for normal force. At this point, the picture I drew over here is kind of busy, so I'm going to go below it and draw my xy axis. I'm going to choose to draw my xy axis in the traditional way, with x being horizontal, y being vertical. Basically, I'm taking this picture and I'm just tilting it a little bit, because when I see an xy axis on a sheet of paper in front of me, it makes me a little more comfortable to see x pointing to the right and y pointing towards the top of the page. So I'm just going to tilt this picture. So I could say here is my x-axis and here is my y-axis pointing straight up. I have the crate at the origin where I chose to draw it. And now what are the vectors? Well, the acceleration vector is entirely along the negative x direction. So the acceleration vector will look something like this. The normal force vector is entirely in the y direction, so I could just draw that over here on this picture. So here is F normal. And the force of gravity, well, in this picture it is straight down towards the center of the Earth, but we tilted our coordinate system. So I look at this picture a little bit closer and I notice the force of gravity is entirely in the third quadrant. And it seems like it's kind of closer to the negative y-axis than the negative x-axis. So the force of gravity will probably look something like this, give or take. So here is the force of gravity acting on the crate. Now, normally, we always had gravity to be straight down towards the center of the Earth, and we had the y-axis to be pointing straight up. So previously, gravity was always entirely in the negative y direction. But as a result of us choosing to tilt our coordinate system, gravity is now in the third quadrant. The force of gravity will have an x and a y component in this particular coordinate system. Okay, let's write out the vectors to some extent. Let's see what we could do with that. So the acceleration vector will have two components, an x component and a y component. So I could choose to write ax is equal to, I do not know what ax is, but I can write ay is equal to 0. For the normal force, I do not know what the amount of the normal force is, but I do know that the normal force will have no component in the x direction. So I could write the normal force in the x direction is equal to 0. The normal force in the y direction, well, the normal force in the y direction is going to be entirely the magnitude of the full normal force vector. So I'll write the normal force in the y direction is equal to Fn, where this is the full magnitude of the normal force. The very last vector that I am going to write out is the force of gravity. So the force of gravity has an x and y component, so I will need to somehow accommodate both of them. The total magnitude, I'm going to leave some space up here. The force of gravity has a total magnitude of mg. So in this case, the mass is 2 kilograms, g is 9.8, the acceleration due to gravity. So mg is equal to 2 times 9.8, which is equal to 19.6. So the force of gravity has a magnitude of 19.6 newtons. In other words, this vector here has a magnitude of 19.6. At this point, this is a chapter 3 breaking a vector into its components question. If this vector has a magnitude of 19.6, what is its x component? What is its y component? So in order to answer that question, we need to know what angle is this vector pointing at? What direction is it pointing in? So to help answer that question, let's go back to this picture. And I'm just going to use some trigonometry. I'm going to think about right triangles to help me see what direction this vector is pointing in. The first thing I'm going to notice is that the ramp looks very much like a right triangle. I could see that here is an angle of 20 degrees, and in the lower right corner of the ramp, this makes an angle of 90 degrees. And if the ramp is in the shape of a triangle, I expect the angles to add up to 180. So 90 plus 20 gives me 110. Therefore, this angle of the ramp in the upper right corner must be a 70-degree angle. Let's look at another right triangle in this ramp. Specifically, let's begin at the crate and let's draw a line straight down along this force of gravity vector until we hit the base of the ramp. So if I draw a line from the origin straight down through the force of gravity and continue down to the base of the ramp, I would see another right triangle right over here, where here is the base of the ramp itself. Now I'm going to travel straight up, and now I'm going to travel along the ramp. And this right triangle is identical to this other right triangle I just drew, where the angle between this vertical line and the base of the ramp is 90 degrees. If I have a 90-degree angle here and a 20-degree angle here, then this angle will be 70 degrees as well. So I look at this picture, I see the force of gravity vector is pointing straight down towards the base of the ramp. The negative x-axis is, if I draw it from the crate, going down towards the bottom of the ramp. The angle between the x-axis and the force of gravity is 70 degrees. Therefore, this angle right over here is 70 degrees. At this point, I have enough information to write out the components of the force of gravity. I would write the force of gravity in the x direction as 19.6, the magnitude of the force of gravity, times the cosine of 250 degrees. When I put that number into a calculator, I get the force of gravity in the x direction is negative 6.7. How did I get this 250 degrees? Well, we said back in chapter 3 that when you are breaking a vector into its components, you pretend you are aligned with the positive x-axis, and then you sweep around until you are aligned with your vector. The vector I'm trying to align with is this vector that is 70 degrees below the negative x-axis. So I would have to sweep around 90, 180, and 70 degrees more. So 180 plus 70 gives me 250 degrees. I could very similarly write the force of gravity in the y direction as F gravity in the y is equal to 19.6, the magnitude of my force of gravity, times the sine of 250 degrees. And when I put that number into a calculator, I find that the force of gravity in the y direction is negative 18.4 newtons. So at this point, I have written every vector in this problem in its individual components. Because AX is currently an unknown that we're trying to find, I'm just going to call this term A. So I'm going to point out right now, I am calling the acceleration in the X direction A. I look at the picture that I drew and I see that the acceleration is pointing in the negative X direction. So I'm going to go through this problem And I expect that when I come to find some result for what the acceleration is, I expect a to be a negative number because acceleration should be pointing in the negative x direction. Similarly, if I go through some type of calculation and I find the normal force, I don't know what the normal force is going to be yet, but I know the normal force is going to be entirely in the y direction. That is why I just chose to write the entirety of the magnitude of the normal force, which I call Fn, is only in the y direction. It is 0 in the x direction. So we can now begin set up Newton's second law and begin solving for the acceleration, the normal force, and all the other parts of this problem. When we work through a Newton's second law problem with two or more directions, I think it is very efficient to write down each component of each vector in your problem. If you have an actual number for the components of a vector, like for example, here we have gravity, and we also have acceleration in the y and normal force in the x, that's great. You have a number that's ready to be plugged in. Even if you don't have a number, it's still all right. We don't know what the acceleration is, but that is one of the things we are solving for in this problem. So we can't know what the acceleration is until we solve this problem. So I'm going to begin by setting up Newton's second law in the y direction. So if I were to write now F net y equals may, okay, the left-hand side of Newton's second law, what are the forces in the y direction? I have the normal force and the force of gravity. I don't need to think at all at this point. I could turn my brain off. I could go on autopilot. I just need to copy what I have written here. So, okay, I have the normal force, Fn. I have the force of gravity in the y direction, negative 18.4, and I set that equal to the mass of the crate. At the beginning of this problem, we said the mass of the crate is equal to 2 kilograms, and the acceleration of the crate in the y direction is 0. So from this equation, I could say the normal force minus 18.4 is equal to 0, and I find the normal force on the crate is equal to 18.4 newtons. Well, we were not asked to find the normal force on the crate, but we found it, so hooray for us. This number is 18.4. Now let's find the acceleration on the crate. To find the acceleration on the crate, I'm going to solve Newton's second law in the x direction. So I'm going to set up F net x equals max. Now, the left-hand side of Newton's second law, again, I could just turn my brain off, go on autopilot. I just need to copy what I wrote in this chart up here. We have two forces in the x direction. The normal force is 0. The gravity force is negative 6.7. So I could write 0 minus 6.7. The mass of the crate, again, is 2 kilograms. And the acceleration of the crate, I don't know what that is. That is just a. When I go through the arithmetic of this problem, I find the acceleration of the crate is negative 3.35 meters per second square. So at this point, I have solved for the acceleration of the crate. The crate will accelerate down the ramp at a rate of 3.35 meters per second square in the negative x direction based on how I drew this problem. Part B of this problem asks us how fast is the crate moving. Now, Part B is not a new type of calculation for this chapter. Part B is just a Chapter 2 1D motion question. If I were to draw the picture I have like this, where I have, here is my ramp, here's my crate. My crate is going to be accelerating at 3.35 down the ramp. So here's the acceleration, a equals negative 3.35 meter per second square. I could choose, well, we'll keep the same coordinate system. So the x initial of the crate is equal to 0. If the crate is 30 meters above the bottom of the ramp, that would imply x final down here. X final is equal to -30. Now, if we say the crate begins at rest, that is like saying V initial is equal to 0. And we are asked what is V final equal to. So at this point, I have enough information to plug numbers in and solve for V final. So I could say V squared is equal to V initial squared plus 2a x final minus x initial. So I could say V squared is going to be 0 squared plus 2 negative 3.35, and x final minus x initial. I need to be careful about plugging numbers in the correct place. So x final is -30 because we chose the origin to be right at the initial position of the crate, and the positive x direction points up the ramp. Therefore, the bottom of the ramp would be at x equals -30. So I could say -30 minus 0. And at this point, I just have to plug in numbers. And I find after I go through the arithmetic that V squared is equal to 201. And from there, I could say then V final at the bottom of the ramp is 14.2. Now, if you are asked what is the velocity of the crate, I would say the velocity of the crate is -14.2 because you're moving in the negative x direction. So the final velocity of the crate is -14.2 meters per second. But this question specifically asks for the final speed of the crate when it reaches the bottom of the ramp. Speed is just the magnitude of velocity. So I could say the final speed is 14.2 meter per second.